Hello, my name is Amir Moghaddam. I'm currently pursuing my master's degree at the University of Alberta in geotechnical engineering with a focus on reservoir geomechanics. I'm also a graduate research assistant in the Reservoir Geomechanics Research Group under the supervision of Dr. Rick Chalaternik, the Energy Simulation Research Chair in Reservoir Geomechanics. Today, I will be presenting my research on scaled physical modeling of geomechanical implications of wormholes during the CO2-based CSI process from water-fluided CHOPS reservoirs. This research focuses on optimizing the CO2-based cyclic solvent injection CSI process for enhancing oil recovery from cold heavy oil production with sand reservoirs, or CHOPS. It addresses the geomechanical impacts of wormholes, a key feature in these reservoirs, and provides insights into improving the efficiency of this enhanced oil recovery method. We will start with background and purpose. CHOPS is a well-known heavy oil recovery method that involves the aggressive co-production of sand and oil, leading to the formation of wormholes, high porosity zones with increased permeability. These zones create heterogeneity in reservoir, causing significant reservoir pressure depletion and affecting subsequent oil recovery methods. Once primary depletion occurs, oil recovery becomes significantly difficult, making post-CHOPS enhanced oil recovery techniques necessary to improve production. Among these methods, the CO2-based CSI process shows significant potential, especially in water-fluid CHOPS reservoirs. My research aims to better understand the geomechanical and hydrodynamic behavior of both wormhole and non-wormhole domains during the injection, soaking, and production cycles of the CSI process. To realistically simulate the complex hydromechanical interactions within the CHOPS reservoir, we took an innovative approach by combining 3D printing and geotechnical centrifuge modeling. The use of 3D printed rock specimens is a novel method that allowed us to accurately replicate the intricate wormhole structures typically found in the CHOPS reservoirs. We designed and printed a 50 centimeter diameter rock prototype, incorporating realistic geological features crucial for studying the wormhole behavior during the CO2-based CSI process. One of the most significant achievements of this research has been the application of centrifuge scaling laws to accurately represent reservoir conditions. By spinning the 50 centimeter prototype at 30 Gs in geotechnical centrifuge, we were able to model a system equivalent to a 15-meter long reservoir. This level of scaling is critical for ensuring that the experimental results reflect realistic reservoir behavior, which can then be used to inform field-scale applications. Our experiments were conducted at the GeoSurf Geotechnical Centrifuge Experimental Research Facility at the University of Alberta, which has been instrumental in making this work possible. GeoSurf is a world-class facility that allowed us to push the boundaries of physical modeling in reservoir geomechanics. The ability to conduct high-G geotechnical centrifuge tests on such complex models is truly groundbreaking and has provided us with a unique opportunity to study the geomechanical implications of CO2 injection into wormhole-dominated reservoirs. The work carried out at GeoSurf represents a significant step forward in physical modeling, providing invaluable data for upscaling and application to real-world field operations. A key aspect of this research is the coupled simulation using FLAG3D and CMG stars. This coupling allows us to accurately simulate both the geomechanical behavior and fluid flow dynamics of the reservoir. FLAG3D handles the geomechanical aspects, such as the stress distribution and deformation, while CMG stars models the complex fluid flow including the behavior of foamy oil during the CO2-based CSI process. The foamy oil behavior is modeled using chemical reactions to replicate the gastric solution and non-equilibrium conditions that occur during pressure depletion. This combined modeling approach provides a more comprehensive understanding of how the reservoir's wormhole interact with the injected CO2 during the injection, soaking, and production cycles of CSI. During the experimentation, one of the challenges that we faced was the limitation of our 3D printing capabilities. We were unable to print a full-scale 50-centimeter sample as a single piece due to the size constraints of our printer. As a result, the sample had to be constructed part by part, which meant the final model wasn't completely unified sample. These deviations introduced potential weaknesses at the boundaries where the pieces were joined, making the physical model more complex and realistic in simulation fractures reservoirs. A key aspect of this research is the coupled simulation using FLAG3D and CMG stars. This coupling allows us to accurately simulate both the geomechanical behavior and fluid flow dynamics of the reservoir. FLAG3D handles the geomechanical aspects, such as the stress distribution and deformation, while CMG stars models the complex fluid flow, including the behavior of foamy oil during the CO2-based CSI process. We observed key pressure variations during the wellbore opening and accumulator filling phases, which will inform the next phase of our numerical simulations. These results highlight the impact of wormhole structures on fluid behavior and provide valuable insights for optimizing the CSI process in terms of injection strategies and well design. The next steps in this research involve upscaling the experimental data using numerical simulation, allowing us to translate the finding to field-scale operations in Alberta and Saskatchewan's CHOPS reservoirs. Our goal is to develop optimized well designs and injection strategies that maximize oil recovery while minimizing environmental impact. By refining the CO2-based CSI process, we hope to provide a viable EOR method that enhances oil production from water-flooded CHOPS reservoirs while contributing to CO2 sequestration effort in Canada. Ultimately, this research will help operators make more informed decisions about well placement, reservoir management, and sustainability. In conclusion, my research aims to improve the efficiency and sustainability of the CO2-based CSI process by addressing the geomechanical challenges posed by wormholes in CHOPS reservoirs. The combination of 3D printing, geotechnical centrifuge modeling, and numerical simulations has provided valuable insights into optimizing this enhanced oil recovery method. In the last part, I wanted to thank my team, especially my supervisors, Dr. Ali Reza, Dr. Rick, and Dr. Gonzalo, and also all the sponsors and industrial partners that made this work happen. Thank you for your time and attention. If you have any questions or would like to discuss this research further, please feel free to reach out to me. Thank you.